Hello, everybody. My name is Sevastyan. I am an Android developer at Muse. I've been writing Android applications for almost 4 years now, and nowadays I'm looking to expand my expertise into mobile security, hence this webinar. I just want to share my first experience of so-called dipping my toes into this vast field. So what I'm going to show you today, to be specific, I'm going to crack two Android applications provided by Mobile Security Testing Guide. Basically, extract a secret string from Java side, which is level 1, and from native code level 2. So I took these applications from the Mobile Security Testing Guide repository. It's from OWASP. So if you go to crackmes folder, there you will find Android and iOS applications, and level 1 and level 2, these ones that are we going to use today. So MSTG then is an online community which produces freely available articles, methodologies, documentation tools, etc., in the field of mobile application security. And these crackmes, these specifically designed applications, are the product of their work. They're created to showcase a particular security problem and how to take the advantage of it. A small disclaimer, what I'm going to show you is not intended for piracy or other non-legal issues, uses, of course. These are the tools that I'm going to use today. ADB, of course, I think you're familiar with it. APK Tool to unpack and repackage the APK archive. Dex to jar to convert Dex files to class files to human readable format. And Java decompiler with GUI to read those files. And for the level 1, I'm going to use Java Debugger. For level 2, GNU Project Debugger, and Katra and Radar 2 for binary patching. So I guess let's start. As you can see, I have already downloaded level 1 application, and I have my emulator running. So let's install it and see what it is all about. Application is installed. Disregard this dialog for now. What we're interested in is mainly the app itself, which is pretty simple. It is a simple input field with one button, verify. So how it works, you just enter some secret, you click verify. If it compares to the secret string, you get success dialog. If not, you get the error dialog. The goal is to find out what that secret is. And the general idea of how to do it is to first make the application debuggable and debug to that point where the input and secret are compared, and log the variables, right? Pretty simple. So let's do it. Let's make the application debuggable first. By the way, I will enlarge my. Okay, I think it's better. To make the application debuggable, we're going to use APK Tool, which is freely available. D for decode, so we're going to decode the archive. I'm going to use the S option because, which means do not decode resources because we don't need them. All we need is the manifest file. I'm going to specify the application and output folder. Great. Let's see what's inside. There is a manifest. And as you can see in the application tag, there is no Android debuggable true, which means that the application is not debuggable. So The way to proceed, like one can edit this manifest with his favorite editor, but since we are using the tool, it provides us out-of-the-box solution. So we can just use APK Tool, build, specify the directory, use the D option, which is very important. It will add this Android debuggable true to the manifest automatically. And we're going to specify the name of our application. So at this moment, we have a original application and debuggable one. The debuggable one will not be installed on the device because it's not signed yet, of course. You can easily verify it with the APK signer. Verify. Let's be verbose. Yeah, it does not verify. So let's sign it. For signing, since it is a relatively complex command, I have created a alias, which is this stupid name. Of course, all these variables are mine variables. You need to substitute it for your own. So this is my key store, this is my key alias, and this is my password. But the command is pretty simple. Or if you prefer to sign it via the Android Studios in some other way, you can do it some other way. Doesn't matter. So let's sign it. Okay, it is signed. And let's install it. Maybe let's uninstall this one and install the new debuggable one. Great. Maybe let's move it here. Yep, app is debuggable. So the application detected that it can be debugged, which is also a security measure against tampering and cracking. So this is a dialog. You cannot click outside of it to close it. And if you click OK, it will exit the application. So the next step for us is to circumvent this dialog, like to bypass these dialogs. And for it, let's dig deeper. Let's look into the source code. For this, we're going to use dex2jar. It's also a type alias. I'm sorry, just an alias for this simple command. So this is from dex2jar toolbox, also freely available. So let's decode our original application. Okay, we now have a jar. And let's look inside with the GUI tool, Java decompiler. Sorry, it does not accept the arguments. We just need to start it. Yep. And now we can open the jar archive. Let's find the main activity. And what's interesting here? Two things. First, this method A, which actually is responsible for showing these dialogues, easily identifiable by this message, this is unacceptable. So looking at this, we can say that in order to close this dialog without clicking on the button and triggering this on-click listener that will actually exit the application, we can change this line. So instead of set cancelable false, we can say set cancelable true. So we can change the variable during runtime, which will make our dialog closable when you click outside of it. So let's do that. For this, we need to first start our application in the debug mode. And yeah, for this, we're going to use the command adb shell activity manager start. I'm going to use D that enables debugging. And I'm going to specify the component, the Android component, which is the package name plus, I'm sorry, yeah, the package name plus the component. And the package name is, let's start the application to find out. This one. So once again, ADB shell activity manager starts in a debug mode, and our component, which is, can I copy it? Yes, I can. And main activity. Let me bring back the emulator. Let's exit. And look what will happen now if I click enter. Yeah, the application starts in the waiting for debugger mode. So it waits for the debugger to be attached to it. Let's attach it. But before we do that, we need to establish a connection, like a socket connection to the device, to our emulator. The command is pretty simple. It is ADB again, ADB forward. We're going to establish a socket connection. On our side, it's going to be TCP 4312. On the other side, it's going to be Java debug Y protocol. And here we need to specify the process ID, which we again need to find out. This is the process ID. And let's establish a connection. And process ID, yeah. Okay, we can easily verify, since I'm on Linux, I can verify that the port is open and listening. I will not explain this command. This is out of scope of this webinar. Yep, we are listening on that port. Great. At this stage, the app waits for the debugger to be attached to it, and there is a connection to the app's process via localhost 4321 port. And let's start the debugger. We're going to use, I go here to the list of tools. We are going to use Java Debugger because we are debugging the Java code. So let's type it GDB connect. We're going to establish a connection to a target virtual machine using a named connector, which is a ComSan JDI socket attach. I'm going to spell the arguments. And running this command will attach a debugger and the application will resume. But with this, the code for setting up the dialog will also run. And we don't want that because we want to debug to this point. So let's pipe down the suspend command to this command. Yep, great. And look what will happen to the emulator. Nothing. There is a mistake. Have I made a mistake in the connector name? No. I have made a mistake in the argument. Host name. Let me bring back it. So enter. Great. All threads are suspended and the application has not resumed, which is what we want. So let's start by passing the dialog. We need to set a breakpoint. We need to set a breakpoint on this line. this method, I should say, which is Android app dialog set cancelable. The way you do it, you just say stop in and specify the method. If the breakpoint is set, you can use clear without the argument to see your breakpoints. So let's resume. Okay, all thread resumed. We have hit the breakpoint. Let's see what we have hit with locals that will print the variables. So we have flag true. And here is the flag false. So this is not the place that we want. Let's resume. Locals again. Flag false. Probably this is the stuff we want. So let's set this flag to true with an easy command flag equals true. Let's resume again. Breakpoint. Flag true. This is what we want. So no action here. Resume. Again a breakpoint. False. So let's change it. Resume. And all threads are resumed. The application continued. App is debuggable. So if I click outside, nothing is happening. I will resume. I have made a mistake. I have in my last comment I said flag false, which should be flag true. So let's exit the application and repeat the process again. So let's start the application. In the wait for debug mode. Let's establish a connection. And start the debugger. Great. Once again, stop in Android app dialog. Okay. So we have flag false, we need it true. So this is not it. Resume. Also, let's change it. Set flag true. Resume. Set flag true. Resume. All threads resumed. And now if I click outside, yes, the first dialog is closed, is cancelled, and the second one also cancelled. Great. So now we have our hands on this input field, which we can now debug. And for this, what exactly to debug? To find out, we need to go to the source code again. And this line is very interesting, which also opens a dialog with the success state. So probably this is what we want. And it opens it if this method returns true. So let's click on it. So this is an A method which gets the secret, deciphers it, and compares it with the input method, with the input string, param string. So it is here. So we can set breakpoint on javalan equals method. But since this method is actually heavily used in Android applications, let's set a breakpoint somewhere before it, just before it, and it will be, let's choose here and this one. So it will be right before this call. So it is cipher do final, and cipher is JavaX crypto cipher. So let's stop in JavaX crypto cipher do final, and since probability is overloaded method, let's specify the argument, which is this one. So it's byte. Okay, let's list our breakpoints. Here they are. Let's resume. But before we resume, let's enter something. Click verify. We have hit the breakpoint. Let's print the variables. This is the breakpoint for. I'm sorry, why we're hitting it? That's unusual. Let's clear the breakpoint for the dialog. Let's resume. We have hit another breakpoint. Okay, that's great. Which means we have hit this place. And now it's safe to set the breakpoint on this method, which is javalan equals. So let's stop in javalan string equals. This is our breakpoints. Let's resume. This is probably not it, because our input is W. And here's the secret to be. So let's try it. Let's clear all the breakpoints. Let's resume. And I want to believe this is the secret string. Yes, this is the one, success. So this concludes the first level. Let's not waste a lot of time and move to the second level, because it will be a little bit harder to crack. So let's close the application and uninstall it. Move it away. Now let's change the folder to the one where I have level 2. So let's install and see this up. So as we can see, it's basically the same application, but it works a little bit differently, and the secret is hidden not in Java, but on the native side. I will show you how that can be deducted. But yeah, still you cannot click outside. The application expects the input string in this field, and there is the same verify button, same dialog that prevent us from tampering with the application. So let's exit. With level 2, I guess it is going to be reasonable if you go straight into the source code. So let's get that jar archive with text to jar. Yep. Let's close this project. How do I do that? Yep. So main activity is the place to take a look first. And immediately, yeah, we can see that it uses the native library. So it loads the library named foo. It initializes it in onCreate method with the init method, which is a native method. So let's find out how it actually calculates the secret, how it compares the secret with the input. Again, we find our familiar dialog with the success title, same condition, but the evaluator is different. So we can see that it delegates to bar, and bar is also a native method. So at this point, we can say that, yeah, the secret is compared with an input string on the native side. So with this application, we need to debug the native code. There is no Java method to debug. But basically what we need to do is to patch this library, this full library. So let's get our hands on it. So at this moment, we have only application and jar archive. Let's use our APK tool to get access to the sources and the library. And for the APK tool, the command is simple. It's APK tool decode application and specify the directory. Let's look inside. So we have a lib folder with a bunch of directories that have names after respective architectures. So at this point, we need to find out what is the architecture of our device, what is the architecture of the emulator. Proper way to do that, and I guess the easiest one, is just to see what's being loaded live. So let's start the app. Let's first know the process ID of it. This is interesting. There are two processes with the same package name. I will explain why there are two of them, but for now, just disregard it. Let's choose the first one, just for the sake of it. So we know I have copied it to my buffer, so we know the process ID. And now let's see what is loaded, which libraries are loaded. Let's get the shell on the device, become root, and see inside. So it's in prods, your process ID, file maps. So there is a bunch of stuff. Let's grab what we want. And yeah, these are the libraries we want. And this is the architecture. So it is our library for architecture is x86. Great, so we know it. So we know what to choose from these folders. So we need x86. Yeah, this one. Next step is to see inside this library, right? So for this, I'm going to use another tool called cutter. I have just a simple executable on my machine. Let's select this library. This dialog is not very important for now. Basically what it does auto analysis with a AAA level just accept the defaults. Okay, so this is the interface. On your left side, you have all the functions loaded by this library. On the right, you have your assembly code. On the bottom, your scroll bar. Let's take a look on the list of functions. What is interesting here is probably the string compare, which is probably used for comparing the secret and the input. We don't know yet. This is just our assumption. Like the easiest way is to debug to this point and see. And what is also interesting, this one, ptrace. Ptrace is a system Linux call used for debugging. So what it does, it attaches itself to Android process. And in Android world, it's only possible for one process to attach itself to an Android process. So basically what it does, it is a security measure from tampering. So even if you mark your application as debuggable in the manifest, you will not be able to debug it because something is already taking the place of a debugger. What we need to do is we need to replace this method, this function. So we need to nope it, and nope is the term for the abbreviation for non-operational. And the way we do it on x86 architecture is by putting a bunch of 90s on the address where this function is called. There are some other techniques for different architectures, so you can consult the manual for them. And in order to make this piece of code non-operational, let's find out where it is called exactly. So 2 places, and the addresses are 777 and 7A7. And I have closed the tool. I didn't want to do that, but okay. So what we're going to do? We are going to nope this the ptrace call. This will allow us to make the application debuggable. For this, we're going to use just a simple hex editor, but actually it's much more. It's radar true. Actually, radar true is what is used by Cutter GUI tool. So W option to open the library in the writable mode. The library is in the decoded lib architecture library. Great. Let's use the same AAA analysis. And let's nope the places we don't want. So it's a bunch of 90s at, and it was 777. And the other place was 7A7. Great, so quit. So at this point, if you look at the library, yeah, it was modified just now, 19.401. Yep. So the app should be debuggable now. What's left to do is to bypass the dialogues, these dialogues. We are not going to do it the same way as we did in level 1. We're going to do it slightly in a different way. And we're going to do it via changing the binaries. But since binaries are not human readable, we're going to change the Smalley files. And Smalley is a human readable format of DEX files. So, and what we're going to need to change, basically the same method A, which shows the dialog. The simple way, I guess, is to make the whole method just empty within empty body. So we will just delete these lines using Smalley code. So let's open it. It says decoded Smalley SG vantage point crackable main activity. Yep. Let's open it in a text editor. And we need to find the A method. So yeah, this is the smaller code. It is human readable. Some crazy folks even programming it, but beware that it's not translated one-to-one to Java and vice versa. So yeah, it's hard to understand, but it's doable, and you can change something here. So yeah, this is the method A. There is a new instance of dialog builder, which is this one. So yeah, this is probably it. So let's just delete this body. Like this, save, exit. So at this moment we have a library patched, which will allow us to bypass the dialogs, and the application should be debuggable. Let's rebuild it within APK Tool. APK Tool, build, decode it. I'm gonna put the debuggable option into the manifest, and the output name, which is Uncrackable to patched. Great. Here it is. Let's sign it. Yeah, the application is signed. Let's delete this one. And install. So yeah, no dialogues for now. And if you look at the process, also one process, which means that our actions were successful. The application is successfully patched, and we can now start the debugging. For this, what we need to debug, we need to debug that string compare function, which is shown in Cutter, which I have closed. So let's reopen. So yeah, I have opened the previous not patched library, so you can still see this p trace. So just disregard it. Let's find out where the string compare is called. Only one place. Great. So we know the address. So what's happening here? We're just pushing some variables, probably input and secret, and we are just comparing two variables. This is the address, but the problem is that it is a relative address to the library. So it's not the actual address on the device address space. The actual address will be the address the library is loaded into plus this one. So what is the actual place? Our application is running. Great. So let's find out. Here I will just copy the process ID, this one, and do the same procedure that I have already shown you. I will just become root on the device and get the procs. Yep. So these are the libraries, our library for, and this is the address space. So lower bound and upper bound. So the actual address will be lower bound, which is this, plus the place where this stuff is called, plus FFB. So let us copy this one and exit. The debugging process is going to be a little bit, I mean, not the process, but the actual setup is going to be different in this case because we are going to use GNU Project Debugger, GDB, and the setup is the following. We are going to need a tool called GDB Server, which is going to reside on the emulator on the device. It is going to attach itself to the Android process, and from there it will pass the debugging information to our machine, to GDB running on our machine. So we need to get this GDB server to the emulator. First, let's find out where it is located. By the way, GDB server was not bundled in the GDB installation package with Debian, so you have to look for it manually. So let's, we need to push this GDB server to the emulator. Which is going to be ADB push, the location of the GDB server, universal system resources, bin GDB server. We're gonna push it to data local temp. Great, it's pushed. Let's log in on the device again. Change to that folder. So here it is. Let's run it so it will configure itself. Yep. Do we have our app running? Yes, we do. And now I have copied the process ID of the app, some steps before it. No, I have not. So let's find out the process ID. I will spawn another shell. So this is the process ID. So now we're gonna need to attach the GDB server to that process ID. And the way you do it is pretty simple. It's GDB, I think it's attach. Yeah. Now let's, if I remember correctly, it's the port first, then attach. Yeah, and process ID. Yep. So it's gonna attach port 888 of the emulator to the process of the application. So yes, we are attached. We are listening on that port. So this shell is not usable. Let's switch to another one. So GDB server is attached. Now we need to establish a connection from our machine to emulator. The command is already familiar to us. It's the GDB forward. I'm gonna use the CPU on our end, same port and same port. Great. At this point, GDB server is running on the device, is attached to the apps process and awaits commands on port 888 of the device. Also, our local machine, port 888 links to that port, 888 of the device. And last bit is to start the GDB on our machine and attach ourselves to port 888. So let's run GDB. It's an interactive command. And let's attach ourselves. Specify the target, which is remote, and the port. It loads a bunch of stuff. If we switch back to another shell. Yeah, we were listening to port, and now we are in a remote debugging from host. Great. Let's switch to another shell. So this is the final part where we're going to set the breakpoints. And yeah, do I have the relative library address? No, I do not. So I need to do it again. I need to find out the library address. Let's spawn another shell. I should have wrote it down somewhere. But do I have? Yeah, I do have process ID. Yep. So let's do a split screen. So this is the library, executable library. This is the lower bound. So the way how you set a breakpoint with GDB is pretty simple. It's b asterisk and your address, which is c1 ad 2 and ffb. Was it ffb? Yeah. And ffb. Not here, here. Yep. Breakpoint is set. Let's quit the split screen. Bring up the emulator so you can see what's going on. Let's put something. Why do? Okay, we are suspended, I guess. Yeah, we need to continue with the C command. Yeah. Oh no, what's happening? We are not responding. So let's do the procedure again. So let's start the GDB server. Okay, we are listening. We need two forwards. And we need to start the GDB. So once more, so we check. We have our GDB server running. Yep. We have our application running, and we're starting the GDB. Yeah. Yeah, we are in a remote debug mode. But something is wrong. Let's continue. Yeah, great. So let's set the breakpoint. And for this, we're gonna need the address space. So I'm setting the breakpoint with B and the address, which is this one. And that would be. So yeah, I do set the breakpoint. Let's enter. Whites. And let's enter something, click verify. Nothing happening. Let's find out why. Let's see into the key, cutter tool. And you can see that above pushing the values to registers, there is also a check for the length of the input string. This one means 33, so let's try 33 character input. And hopefully it will work. No, it doesn't. That is the problem. I think I have something wrong with my GDB. Yeah. So now there was another process attached to this shell. I don't know why. So I have just clicked Control C. So yeah, now we have hit the breakpoint. Let's see what the variables are with a simple command info registers. So this is how our registers look. We need to find out what the registers are that are used for comparing the secrets. Let's get rid of the emulator. So it's ESI. ESI is here. And the way you dump the values is with the XS and the address. So yeah, this is our input. Some weird one, probably the escape characters or something. And EAX. Yep, that is the password. Thanks for all the fish. Let's continue. Let's try it. Just to be sure. We have hit the breakpoint again. Let's continue. Yep, success. This is the correct secret. And that was level 2. Yeah, we have finally succeeded in cracking this. So yeah, this is the end of my webinar. I hope you have enjoyed it as much as I did. So to sum up what we have done, what's the procedure for cracking these two applications was. The main idea is to make the application debuggable, and then you just need to analyze the code. And this is not trivial. Like there is some art to it. You need to find a place that needs to be changed in order to achieve your goals. The rest of it is just to repackage, debug, and make profit. So yeah, I hope you have enjoyed. I think we have time for questions. And thank you. Feel free to follow me on my Twitter and connect with me via email.